Okay, yes, in the last class we were discussing about curves. Okay, right? So whenever you hear the word curves, right, it doesn't mean that anything which has some bended shape. Okay, right? Usually what we call it as a curve, right? Whenever a curve word comes into our mind, right, what we think is, right, curves is nothing but it has some portion, right, bended portion, right, that is called as a curve. But actual technical definition of a curve according to the computer graphics is fine, right? They tell curve, right, is nothing but joining the set of points on the plane, right? Whenever I have a set of points, that points may be straight or that points may be in the form of curved fashion or anything. Okay, random fashion, anything, right? If I join those set of points, then I call that as a curve. Or drawing on a plane, that is drawing on a plane without lifting my writing object, that is pen, right? We call that as a curved surfaces, curves. Okay, right? So and we also discussed this, right? The curve representation, right? Curve representation are of basically two types. One is parametric representation, another one is non-parametric representation. Okay, non-parametric representation in the sense, right, those involves explicit representation and implicit representations. Okay, parametric representation means, right, I will represent each of these x, y and z of a particular coordinate as a function of something. Okay, right, you have not heard these type of representation anywhere, right, where you say x, y and z, the x, y and z axis of a particular point, right, of a particular coordinate, right, in some, with some function with respect to a parameter. Okay, right, what you have seen till now, right, x, y, z, right, it is the direct values. Okay, right, so any representation till now, right, we have seen x, y, z as a direct values, right? You give x, y, right, I can plot a point, fine, right? That is what you have seen in explicit representation, that is what you have seen in implicit representation, that is non-parametric representation, where I don't use any parametric functions which use with the help of that is the function which uses some parameters. Okay, right? So but usually whenever we talk about a curve, right, we represent the curve, right, with parametric representation. That is, we parametric representation means that should directly strike into our mind that, right, x, y and z, okay, axis for a coordinate will be represented in the function of something. Okay, not direct values as till now, as what we are seeing till now. Okay, right? So today we will also see an example for this parametric representation of a curve, right? How we will represent a curve with the help of a parameter. That is also you will see it today. Fine, right? So parametric representation, a simple example for parametric representation is this. Okay, right? Where, okay, if this is a point, right, where the starting of the point is p0 and the ending of the point is p1, right? So parameter, I represent this with a parameter t, where t is equal to, t will be 0 at the starting and t will be 1 at the ending. Okay, right? So now if I want to represent this point p, this point, right, which I call that as pxy, right, pxy, how do I represent, right? Yes, so for example, this may be at 0.8, that is my what is my that is my parameter. Okay, right? So how do I represent that point pxy? Fine, it is 1 minus t into, it is 1 minus t into p naught plus t into p1. This is how I represent. Okay, using parameters, parametric representation. Fine, right? So now the first type of curves what we will be seeing is, right, we will be seeing quadric surfaces, right? So what do you mean by quadric surfaces? What do you mean by quadric surfaces? Quadric surfaces are something, right, which will be curved surfaces, right? Parametric form, non-parametric form, this all things we have discussed. Right now the thing is curved surfaces, right? A frequently used classes of objects is curved, is quadric surfaces, which are described by second degree equations, which are described by second degree equations in the sense, right? So these are consider your straight line equation is y is equal to mx plus c. Okay, right? Y is equal to mx plus c is a single degree equation. Okay, right? Because y is of single degree. Okay, right? X is of single degree. Fine, right? On the same lines, when you come for circle or sphere, right, whatever you call, what is this, x square plus y square minus r square is equal to 0. Okay, right? That is a second degree equation where you are representing that equation with squares. Okay, right? So whenever I talk about quadric surface, right, all the quadric surfaces are represented with second degree equations, right? Second degree equations means that should come to your mind is, right, all those things are described using squares. Okay, right? So now the first type of quadric surface is sphere. Okay, right? A simple they will ask you write a short notes on quadric surfaces. Okay, right? At that time you should write what a quadric surface is, right? A quadric surface means those are the objects which are usually described by second degree equations, right? And any two quadric surfaces you should explain. Okay, right? So in detail you need to explain any two of the quadric surfaces. Fine, right? So now we shall come to the first type of quadric surface. First type of quadric surface is a sphere. Okay, fine, right? So sphere or circle, right, both are same. Fine, right? Both are same. Only difference with respect to my circle and sphere is whenever I talk about circle, right, I talk about two dimension. Okay, right? So the representation of circle and sphere are almost the same. Only difference with respect to circle and sphere is whenever I talk about circle, that circle is a two-dimensional figure. Okay, two-dimensional object. Fine. While whenever I talk about sphere, right? So sphere I talk in terms of three dimension. Both are round in shape. Okay, right? That is what the property of a circle or sphere. But the only difference is circle is two-dimensional, sphere is three-dimensional one. Okay, fine. So now, as it's a three-dimensional one, right? What is the equation of that sphere becomes is, right? Sphere it becomes is, right? X square plus y square plus z square minus is equal to r square, right? Usually, whenever I talk about circle, right? What is the equation of circle? It is x square plus y square minus r square is equal to 0. Minus r square means, right? If we bring that to RHS, it becomes is equal to r square. Fine, right? So here another parameter or another axis gets added, that is your z axis. Okay, your z axis gets added. Fine. So hence we call that as a sphere, and the equation for that is x square plus x square plus y square plus z square is equal to r square. Okay, right? So now how do I represent x, y, and z? Right? I represent x, y, and z in the form of this: x is equal to r cos phi cos theta, y is equal to r cos phi sin theta, and z is equal to r sin phi. Okay, right? So how they are giving this formulas is, right, now consider this is a three-dimensional axis, three-dimensional Cartesian coordinate that I am representing. Okay, right? It is three-dimensional Cartesian. It is three-dimensional Cartesian three-dimensional Cartesian coordinate. What we are representing, fine, right? So there, right? So this is x-axis, y-axis, and z-axis. Okay, this is x-axis, this is y-axis, this is z-axis, right? So now on this surface, right, with respect to z-y plane, right, if we take any point P is the x, y, z. Okay, right? So now whenever I say P means it is a point, right? So P is a point means I need to represent in terms of x, y, and z. Fine, right? Whenever I take P, which is the form of x, y, and z, right? What is x, what is y, what is z? Okay, x, see here, right? So if I take any point P, right? If that point P, the distance between the origin and that point P becomes r, okay, right? And this angle is phi, and this angle becomes theta, right? Then they represent x is equal to r cos phi cos theta, y r cos phi sin theta, and z is equal to r sin phi. Okay, right? So how does that representation comes, right? It is a mathematical thing, right, that they are not given in your syllabus. It is a very deep concept of mathematics which consists of spherical coordinates and all those things, right? I don't want to explain those things as of now, right? Only thing what you need to know is, right, yes, I have xyz plane, right, in which in where I have taken a point p, right? Well, I have taken consider a point p which is at the distance r. Okay, fine, right? So that point p, whenever I say point p, it is nothing but x, y, and z coordinate. What is x, what is y, what is z? Okay, right? That is what you need to remember. Fine, right? So now the next type of quadric surface, right? Quadric surface. As soon as I say quadric surface, you should remember that that quadric surface is of second degree polynomial, second degree equations, right? Second degree equations means x that will be in the form of squares. Okay, right? So what is the next type of polynomial is, right? The next type of polynomial what we will be discussing is ellipse or ellipsoid. Fine, right? So now what is this ellipse or ellipsoid we consider? Okay, right? What becomes ellipse and ellipsoid? What is the difference between a sphere or a circle, a sphere and ellipse? Right? Any example for any example for ellipse? You can tell. See, this is a diagram of ellipse. Okay, right? So how the square and ellipse differ in their representation? Any idea? Right? Any idea that you can give in terms of technically? Right? So sphere and ellipse, right? If I say, okay, as soon as you see the shape, right, you will say, right? Technically, any differentiation between ellipse and sphere, right? A best example for your ellipse is a rugby ball, right? You know rugby ball, how it will be, right? That is the best example for ellipse. Okay, right? So now, how do that ellipse and sphere differ? Fine, right? We shall see it here, right? So whenever I say sphere, sphere is nothing but x square plus y square plus plus z square is equal to r square, right? That means x square plus y square plus z square is equal to r square in the sense, right? So the radius is same. Okay, right? See here, the radius is same, right? From whichever point from the origin, right, to whichever point on the sphere you take it. Okay, right? Whichever point on the sphere you take it, the radius will be same, but that is not the case in terms of ellipse. Okay, right? So in terms of ellipse, okay, right, how do I represent an ellipse equation? I represent an ellipse equation like this: x square divided by rx square plus y divided by ry square plus z divided by rz square is equal to 1. Okay, right? So that means the radius, there are three different radius. There are radius along x-axis, there is a different radius along y-axis, and there is a different radius for z-axis, right? That is what it makes a different from sphere. Okay, right? Sphere means only single radius, only one radius, right? From origin to any point on the surface of the sphere, right? But ellipse is not like this, right? From the center point of the ellipse, right, is the what is that? The radius is not same on the surface of ellipse, right? For example, consider this point, right? So from this point to this point, you have separate radius. From this point to this point, you have separate radius, and from this point to this point, you have separate radius. That means the radius changes along x-axis, radius changes along y-axis, and radius changes along z-axis, right? So this thing, right, you can clearly imagine a rugby ball. Okay, right? So if you just imagine, if you clearly imagine a rugby ball, right, you get a clear clarification of this ellipse and sphere. Okay, right? So that is why you represent ellipse by three radiuses: along x-axis, along y-axis, along z-axis, right? No, so see here, this is a clear difference that they have given, right? So So where, right, see here, right, so from here to here, this is the radius along z axis. Okay, right, so this is the radius along z axis, means, right, this is the ellipse along z axis. Okay, right, now coming to y, this is the radius along y axis. There is a clear difference between z axis, radius along z axis, and radius along y axis, right, and this is what the circumference that comes along y axis. Okay, right, and this is the radius along x axis. X axis radius is different, y axis radius is different, and z axis radius is different, right. For this rx, this is what you will get. Okay, right, so different radiuses along x axis, different radius along y axis, and different radius along z axis, right. This is what your ellipse is, right. So now whenever I take any point on the ellipse, okay, right, so what does that x, y, and z coordinate of those points represent, right. So x, y, and z of those represents, right, x is equal to rx cos phi cos theta, ry cos phi cos sin theta, and z is equal to rz sin theta. Okay, right, this is x, y, and z of any point on a ellipse represents. Okay, fine. So now coming to the next type, right, what is the next type is torus, right. So what is the what is the shape of the torus, right. The torus is nothing but a donut shaped object. You have seen donut, right? Whenever you go for a coffee day or somewhere, right, you can see donut, right. How the donut will be, the donut will be somewhat like a tire, the tire, or sorry, tube. Okay, right, donut shape means, right, it is almost same as almost the same as a tube, right. Tube means, right, it may be a car tube or cycle tube or any of tube, right. How it will be, right, so it will you on the center, right, this is a donut. Okay, right, this is a center, right, where the center you will be having a hole. Okay, right, and from this center, right, from to this circumference, it will be covered with rubber, whenever you consider a tube. Okay, right, or if you consider a donut, right, so on the center point you will be having a hole, right, or you will be having a space, right, and from this point along the circumference of the outer circle, right, everything will be filled with some chocolate, cream, cake, uh, hot chocolate, syrup, all those things, right. This is donut. Okay, right, this is another representation of my quadric surface, which I call it as torus. Okay, right, what is the equation for my torus is, right, so it is z square plus, right, y minus r axis square. Okay, right, so r axis square in the sense this one. Okay, right, r axis square, right, plus z square is equal to r square, right. That is the simple representation of torus, that is donut shaped. Fine, right. So now once we come across with these type of spherical surfaces like sphere, like donut, right, and like the other thing what we saw was ellipse, right. Now let us see how to write a free-handed curved surfaces, right. A free-handed curved surfaces in the sense, right. Come to this. Free-handed curved surfaces. Yes, this is a free-handed curved surfaces where I can write like this, where I can write like this, where I can write like this, right? Where I can write curve like this, where I can write curve like this, right? All these type of writing the curves, okay, right? Don't consider these things, okay? Only consider this writing these curves types, okay, right. So now, yes, whenever with the free hand manually I can write any type of curves. Okay, right, I can write a I can write which has a single curve, right? Or I can write the one where I have two curves. Here is one curve, and coming to here I have another curve. Okay, right? So, and I can write the curve like this, right? I can write the curve, I can write a free, I can write a free-handed where I have three curves, one curve here, one curve here, and another curve here. Okay, right? But how to represent that in a programmatic way? That is our main area of concern, right? By hand I can write it in any manner, there is no problem, right? But when it considered, but when I come for writing a programmatic approach for that, right, it is like, it is as simple as writing a line. If I write a line, right, so yes, it is very easy from a free hand, right? The same thing if I want to write it in the form of a computer coding, right, we had many steps. The same with respect to circle. Okay, right? On the same lines now with respect to curves. Okay, right? So how to write this type of curves, how to write these type of curves, or how to write still narrow curves, or how to write the curves where we find curves at two parts, where we find curves at three parts, right? How to write these type of curves? Okay, right, is our next question. Fine. So now these type of curves where it came, right? So with the practical implementation of these curves, okay, right? The practical implementation of these curves, right, came while they were manufacturing automobiles. Okay, right? Whenever it came into the manufacturing of cars on the ends, right, there will be a curve. Correct? A headlight atra curve irutte. Fine, right? And the same thing when you come for manufacturing of the aeroplanes, right? You will be having a curve in the front. Okay, right? So aeroplane tip, aeroplane mouth, right? It is a curve. Fine, right? Now, how to design that curves? Right, that was a major difficulty what they faced in the early 60s. Okay, right? So this curves, right, are mathematically writing a curve, or once I found a mathematical solution for writing a curve, right, that mathematical solution I can convert that to my programming. Okay, right? That was not a very big task for others, for a programmers, right? What mathematically it will be there, right, to convert that into programming, right? That was not a big task for any programmers. Fine, right? So now I should find a mathematical way of writing any type of curve. Okay, right? So now, yes, this was actually okay, right? Writing such type of curves, right, was developed by Bezier. Okay, right? So Bezier, right, who was Bezier, right, in I think France. Okay, right? So he was research head at Renault Automobiles, right? You know Renault. Fine, right? He was a researcher at Renault Automobiles. Fine, a mathematician, Bezier, right? Who came, who started or who found out this mathematical approach of writing a curve. Okay, fine, right? So so that curve was named after him, Bezier. Okay, and it was not simply called as Bezier curve, right? So it was called as Bezier spline curves. Okay, right? So from where did this word spline came into effect? Okay, right? That was our next question. Fine. How did this spline word came? Right? Spline is nothing but, right? So if a curve depends on the control points, right? Control points was called as spline. If our curve depends on control points, such type of curves were called as spline curves. Okay, and this special type of spline curves was invented by Bezier, and hence it was called as the Bezier curve. Okay, right? What do you mean by whenever I say a curve depends on control points? A curve depends on control points in the sense this is what? Okay, right? Control points means points. Okay, fine, right? If I have number of points on a plane, right, and if the curve completely depends on those points, okay, right, that means a curve obeys those points, right, then we call such type of points as spline curves. Fine, right? You can see here, right, there is a clear cut relationship, or we can see that, right, my curve is clearly following the, okay, my curve is clearly following the points on the plane, right? See here, I had only one point. You can see how the curve is, right? 1 2 3, there are 4 points, right? You can see how the curve is. You can see that, right? So 1 2 3 4 points, right? You can see another type of curve. When you have 1 2 3 4 5 points in this which are spread on this manner, right? You can see how the curves are, how the curve is, right? So something, my curve is obeying my points. Okay, right? Such a type of curve is called as spline curves. Okay, right? And there are two types of spline curves. One is Hermit spline curve and another one is Bezier spline curve. Okay, right? We don't have Hermit spline curve, so I don't explain anything about that, right? What spline curve we have is Bezier spline curve, right? So Bezier spline curve is a type of spline curve. Spline curve means, right, you should get into the mind that, right, spline curve, spline means, right, which depends on the points. Okay, points, we call that as control points, right? A technical term they will give it, right? So they call that as control points, right? Whenever my any curve depends on the, or depends or follows, right, the points on the plane, such type of curves are called as spline curves. Okay, right? So now when we call that as a Bezier spline curve, right, we call that as a Bezier spline curve, right, whenever my curve, okay, right, is within the convex hull of the control points. Okay, right, see, this is the convex hull, this is a convex shape, right? Convex to concave, fine, right? This is a convex shape, this is convex shape, this is convex shape, this is convex shape, fine, right? So now if my, this is, so this whenever this is a convex shape, right? So this complete part becomes convex hull. Convex hull ಅಂದ್ರೆ convex volume ಅಂತ ಅಷ್ಟೇ, convex shape ಒಳಗೆ, fine, right? So now when I call spline curve means which follows the control points, right? When I call a spline curve as a Bezier spline curve, right? So the first point when I call my spline curve as a Bezier spline curve is, right, whenever my curve, okay, this is the curve, right? Whenever my curve is within the convex hull of the control points, right? See, this is the curve, right? This curve is also under the convex hull, that means convex portion, right? So this is the curve, right, where this curve is, this part of the curve is under this convex portion, and this curve is under this convex portion, right? So whenever my curve is under the convex portion, technical word they call it as convex hull, right? Whenever it is under the convex hull, okay, right, of the control points, I call such a type of curves as Bezier spline curves. And the second point for a spline curve means, right, which follows the control points. And the second point for which I'm supposed to call a curve as a Bezier spline curve is, right, whenever I write a curve along the control points, means along the points, right, it should compulsorily touch the starting point and the ending point. Okay, there is no hard and fast rule that, right, whenever I draw a Bezier spline curve, right, that curve should go through all the points on the plane, right? All the points on the plane. There is no such hard and fast rule that it should go through all the points on the plane, right? So my Bezier curve is called as a spline curve, right? Whenever it follows or whenever it passes through the starting point and the ending point, that is enough. I call that as a Bezier curve, right? Whereas coming to the Hermit curves, Hermit spline curves, right? Hermit spline curves, right? So they have to, the property of Hermit spline curve is they have to move through all the control points. If even one control point is missed, right, so then such type of curves will not be is not called as Hermit spline curve, right? The applications of that are different. I don't want to discuss that part, right? Only a simple example I told you. What is the difference between Bezier spline curve and Hermit spline curve? Fine, right? Spline means control points. which follows the control points, right? So now coming to see this example also, you can clearly see that, right? So this is touching the first point and last point. That's it. This is also touching the first point and last point, right? It doesn't touch us all the points on the plane. It doesn't touches all the control points on the plane. Fine, right? And the third property of my Bezier spline curve is, right, so the curve completely depends on the control points. Okay, right? So how the control points will be spreaded, the curve will be like this, right? See here. Here also I have 1, 2, 3, 4 control points, right? So these control points are arranged in some fashion. Okay, coming to this, these control points are arranged in some fashion, right? So based on these control points, right, I have got the curve like this. Based on the arrangement of these control points, I have got the curve like this, right? So my Bezier spline curve completely depends on the arrangement of the control points. Okay, right? First property of my Bezier spline curve, it will be completely inside the convex hull of the control points. Okay, second property, it moves through the first starting point and the ending point, right? Intermediate points, it is option, it can touch that intermediate points or it may not touch that intermediate points, but it cannot go beyond that intermediate points. It should be within the intermediate points curves. Okay, right? And the third property says that, right, my curves completely depends on the arrangement of the control points. Okay, right? So now see here, curve, right? This curve is somewhere, this curve is another design, this curve is in some other design, this curve is in some other design, right? So now whenever I want to represent anything on the anything mathematically, I represented that with equation, right? Straight line I represented that with equation, circle I represented that with equation, sphere I represented that with equation, right? So ellipse I represented that with equation, right? So now what is the equation for these type of curves? Right, see here, why I'm talking about this is whenever the automobile industry became very much uh, that is it got a high boosting, right? Lot of different types of vehicle came into existence, right? For example, whenever we talk the basic what is that basic version of my vehicles, right? The curves will be something, that vehicles will be very small, right? On the same lines, whenever I talk about very big vehicles, right, the curves on the front curves, side curves, right, will be some other way, right? So it is not always the same type of curve, right? Whenever I take circle, right, it is the same type of curve, right? Whenever I take sphere, it's the same type of curve. Whenever I take ellipse, it's the same type of curve. But in these type of curves are not same type. This is this way, this is this way, this is this way, this is this spreaded across, this is one type of curve, right? Now what is the equation for representing such a type of curves, right? That is what Bezier thought about. Okay, right? What Bezier thought about, right? Bezier thought about, okay, right? What equation I can give for these type of curves. Okay, right? So fine, right? So what he did was, right, okay, I cannot give a general equation for this type of curves, right? So what I can give is, right, what I can give is, right, I can give a formula, right, based on the parameter. Okay, right? Based on its parameter, I can give the equation, right? Based on the parameter, in the sense, right, if I take a simple car, okay, Swift or anything, right, their curves are different parameters. Okay, right? On the same lines, if I take some bigger vehicles like aeroplanes or any of those things, right, their parameters are different. Okay, right? So now that is why, right, so this parameter type of equation came into existence. Okay, right? This parameter type of parametric equations came into existence. Okay, where I need to represent the curve for different parameters, taking different parameters. Okay, right? If I take a simple bicycle, right, for mudguard there is a curve, right? That simply depends on x and y. For example, when we take for aeroplanes, right, that may depend x, y, z, and some angles, everything parameters. Right? That is why this parametric equation came into existence, and the general equations what they gave for this type of Bezier curves was this. Okay, right? So pu, right? Pu, it is nothing but a positional vector. Vector means, right, it is a set of points throughout the curve, right? What are those set of points throughout the curve? So set of points throughout the curve andre, right, it is like array. Okay, right? So what are those, what those vector consist of? This vector consists of these formula. Okay, for k is equal to 0 up to n pk. Okay, base year of this is called as, right, that is the blending function. Blending function means which gives the smoothness or which gives the curve shape, right? That completely depends on this. Okay, right? So this one depends, this one gives the complete smoothness of the curve or continuity of the curve. Okay, it should not be sharp, right? It should be smooth curve, right? So those type, those continuity or those smoothness will be given by this parameter bz. Okay, then what is this bz state, right? Complete parameter for my Bezier curve is this equation. Okay, right? So in this pk is different, right, and this complete part is different, bz knu. This is called as uh, blending equation. Blending equation means, right, which gives the continuity, that means which talks about the smoothness of the curve, right? What is that bz tells about? Bz of bz of k comma n tells, right, it is nck, right, combination nck u to the power of k 1 minus u to the power of n minus k. Okay, fine, right? So this p of u means, right, it is a vector throughout it, right? For example, we have a curve is here, right? If we have a curve like this, right? So now those points should be here, right? Complete points. Okay, right? What I call these set of points? I call these set of points from p0 to p2 as a vector, right? Fine. A vector means it is a sequence or array of points, right? So now whenever I take, this is p0, this is p1, this is, if I go like this complete here, right? So each of these are points. If I say each of these are points, right, now then each of these should be having, each points on this should be having x, y, and z. Okay, right? So now what is those x, y, and z on each representation tells, right? So now x of u, y of u, z of u, right? Each point, that is p, which represents x, y, z tells x is equal to, right? So what is p equation? You have that xk into Bezier of k comma n of u, right? So and y of u and z of u tells same thing. Okay, right? So now Bezier of k comma k, what is k comma k? What is Bezier, right? So this blending function of k comma n, if this n is represented by k, if n is replaced by k, right? So what is the answer you get, right? Bezier of k comma k is equal to u into k, and Bezier of 0 comma k. Okay, fine, right? What is Bezier equation? Bezier equation is, right, see, 0 comma k. Now instead of k it is 0, instead of n it is k. Fine, right? So what is the value of base this blending function Bezier of k comma n? Bezier of k comma n for 0 comma k is 1 minus u into k. If you simplify that, you will get that answer. Fine, right? So now what is the, this is a very important concept, Bezier spline curve, because this curve gives us the concept of entire type of curves that will be there. Okay, right? So now if what is the control point, what does those control points refer, right? See, if I have 3 control points like this, I will get the curve like this. If I have 4 control points like this, I will get the curve like this. If there are 4 control points like this, I will get the curve like this. Okay, right? If I have 5 control points like this, I will get the curve like this. Okay, now, right? So now what question they will be asking is explain Bezier curves, right? Explanation of Bezier curves is this Bezier equation, everything you will explain. Okay, right? So now write or give the equation, right? Give the Bezier curve equation for 4 control points. Okay, right? Whenever you have 4 control points, right, give the Bezier curve equation, right? 4 control points in the sense, right, I'm talking about these type of things. Okay, this is 4 control points. Okay, right? Wherever may be the control points, right? I need a general equation so that it represents the curve, how it represents the curve, right? Whenever I have 4 control points, right, how do my Bezier curve looks? Okay, right? Or what is the equation for my Bezier curve, right? What is the equation for the Bezier curve? Equation for Bezier curve is this, right? Positional vector means complete vector of that curve, complete points of that curve, right? This is the complete equation where b c z of k comma n of u represents this, right? So now whenever they give you four right, whatever, what is the question, right? Give the Bezier curve equation for 4 control points, right? For 4 control points in the sense, okay, right? For 4 control points in the sense, for k is equal to, what will be the value of n for 4 control points? K is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3. That means, right, n should be equal to 3 for 4 control points. Okay, right? That means the degree of polynomial is equal to n minus 1. Always, right? The degree of polynomial is equal to n minus 1. If there are 4 control points, right? So I should move from k is equal to 0 up to 3. Okay, is this clear? Right, now let us see what is the equation for Bezier curves for 4 control points. Okay, this is a very important part. Yes, right, you can see this here, right? So Bezier curve representation equation. Okay, what is Bezier curve equation? P of u, that is the positional vector. Okay, right, is nothing but k is equal to 0 to n pk into, right, pk into what is that, Bezier b z of k comma n, right? What is that b z of k comma n? It is nothing but nck into u to the power of k into 1 minus u to the power of n minus k. Okay, right? So that is nothing but from k is equal to 0 to n, right? So pk into nck is nothing but n factorial divided by n minus k factorial into k factorial into u to the power of k into 1 minus u to the power of n minus k. Okay, for 4 control points. Okay, right, when they give for 4 control points, or they may ask you for 3 control points, 2 control points, right? This is a guaranteed question, right? Give the Bezier curve equation for 4 control points or 3 control points or something. That is why I have solved it in a paper and I am explaining you this. This explanation is nowhere in your notes or nowhere in your program, sorry, nowhere in your textbook. Okay, right? If the number of control points is 4, right? So what is the degree of polynomial? Degree of polynomial becomes n minus 1, that is equal to 3. That means from k is equal to 0 up to n is 3 value. Okay, I need to go on representing, right? So that means degree of polynomial is 3. Fine, right? Now how do I expand that? Right? It is p naught, right? This I'm expanding. Pk means, right, now k is equal to 0 up to 3 I need to go. So p naught, okay, p naught into 3 factorial by 3 minus 0 factorial into 0 factorial. That is this p naught into Bezier of 0 comma 3 u plus p1, okay, into P0 of 1 comma 3 k comma n into u plus P2 P of 2 comma 3 into u plus P of 3 into 3 comma 3 into u, right? If they give number of control points is equal to 3, then the degree of polynomial becomes equal to 2. Okay, then you should go up to only this much, right? P naught B of 0 1 comma 2, P of 1 this is B of 0 of 1 comma 2 and P2 into B of 2 comma 2. That's it, you need to end there. Okay, this is polynomial, number of degree is 3, right? So because number of control points is 4, so I'm next going to the next also, right? So now how do I expand this, right? This is P naught, P naught, let it be here only, right? B of 0 3. What is B of 0 3? This is B of 0 3, right? B of 0 3 means, right, n factor, that is n factorial divided by n minus k factorial into u to the power of k 1 minus u to the power of n minus k. So this becomes 1, right? U to the power of 0 is also 1, so 1 minus u cube is 1 minus u cube. On the same lines, right, if you expand b1 of 3, right, b1 of 3 of u 3 factorial divided by 2 factorial into 1 factorial into u to the power of 1 into 1 minus u square, right? That becomes 3 into u into 1 minus u square, 3 into u into 1 minus u square, right? Like this, b of 2 comma 3 also I have given here, right, which I will share it in Moodle, right? This particular problem, right, writing the Bezier curve equation, right? So you just go through that equation and this is a guaranteed question, right? They will ask you for giving the writing the Bezier curve for control points 4 or control points 3 or control points anything, right? Usually they give for control points 3 and control points 4. I have given for control point 4 if there are control points 4. Okay, right? So now this is what I get a general at final P of u, right? P naught into 1 minus u cube plus P1 into 1 minus u square plus P2 into this 1 minus u and P3 into u. Now what is the each component x, y and z component at each P? Is nothing but, right, represent this that is x of u, y of u, z of u, right? Instead of I'm replacing p by x. Wherever there is p, I represent that by x, right? P naught is x naught, p1 is x1, p2 is x2, p3 is x3. On the same lines for y, y naught, y1, y2, y3 and z. Okay, right? This complete thing you need to write it in examination. This formula you should know, right? What is the formula for Bezier curve equation? Next, this b of k comma n, this blending function, continuity function, right? The continuity function is b of k comma n is nck into u to the power of k into 1 minus u to the power of n minus k. nck you need to expand, right? And you, based on number of control points, you need to decide the degree of polynomial, right? From 0 up to the degree of polynomial, you should expand this equation. This equation, right, you need to expand from k is equal to 0 to degree of polynomial n minus 1. Okay, fine, right? I have expanded this, right? So I will share this in Moodle, right? You can check it out and you can do it. Okay, this completes your fourth module. From the next class, sorry, fifth module. From the next class, we shall start fourth module. Okay, thank you.